How you doing, Year 10s? Welcome to another video. These videos are on Unit 2, what are the bonding models. Make sure you've got pen, pencil, highlighter, highlight all the highlighting, copy down all the annotations, make sure that you've logged on to EduCanon and answered all the questions. Now let's get into these videos. (2.4b) How are the properties linked to atomic structure? Covalent bonding. And this video we extend what we did in the last video where we look at double and triple covalent bonds. We explain a few of the properties in terms of electrical conductivity and state at room temperature, and then we compare and contrast all the models we've looked at so far. So in the previous video we looked at drawing the Lewis, the electron dot structures of simple main group molecules. In this video we extend that knowledge into drawing the shapes of things with double and triple bonds. So a single covalent bond was the sharing of 2 electrons. However, we can have more electrons being shared between the atoms to form double and triple bonds. So for instance, oxygen, O2, each oxygen has 6 electrons in the outer shell, so it wants to share 2 electrons. So if another oxygen atom come along that wants to share 2 electrons, we could get a sharing of 4 electrons. And that's what happens in the oxygen molecule. Oxygen will share both of its electrons with another oxygen, having 4 electrons in the bond, which gives us a double bond. 4 electrons bonded together gives us the octet. Each oxygen has 8, but it also gives us a double bond. When we draw that, we have the oxygen and then our double bond, which looks a little bit like an equal sign, and that shows us the structure. Remember that we have the non-bonding electrons as well, so the bonding electrons are the double bond and the non-bonding electrons are the electrons that don't involve the bonding. So here we have our oxygen with our double bond between the other oxygen, and it is in a straight line, so it is a linear shape. Carbon dioxide, the one that students always get wrong. They always get this one wrong. Here we have a carbon that wants to share 4 electrons. We have oxygens that want to share 2 electrons. Now the formula tells us that we need 1 carbon and 2 oxygens. So the only way this can work is if the carbon shares with 1 oxygen and then shares with the other oxygen. So 2 of the electrons could be shared with 1 oxygen, the other 2 can be shared with the other oxygen. So the carbon is in the middle and it shares 2 electrons with 1 oxygen and then 2 electrons with the other oxygen. We have our oxygen electrons in the black, and now I'm going to go through and put in the carbon electrons, which are in the red. So it shares 2 electrons with both, giving it 2 double bonds. We have 2 double bonds between the carbon and the oxygens, and this is described as a linear molecule as well. Ethene has the formula C2H4. So we have 2 carbons and 4 hydrogens. Each hydrogen can only share 1 electron, so it will be at the end of the molecule. The carbons, well, they can share 4 electrons. So what will happen here is the carbons will be joined together and then the hydrogens will be coming off the carbons. So here we have our 2 carbons. You can think of it like 1 carbon has to have 2 hydrogens, the other carbon has to have 2 hydrogens. So we can put in those hydrogens. Hydrogen wants to share 1 electron with the carbon, so I'll put in those electrons as well. And then I can put in the carbon electrons, which are sharing, which are in the red. So here are the 2 carbon electrons. So how many electrons does that leave each carbon with? Well, it leaves it with 2. So those can share 2 electrons between each other, giving us another double bond, which has the formula CH2CH2, which is overall CH4, and we will describe that as being linear, C2H4. Now if we have a look at a triple covalent bond, a sharing of 6 electrons, 6 electrons is a triple bond. Nitrogen is one that does this very often. We have a nitrogen which has 3 electrons to share. If another nitrogen comes along with 3 electrons to share, those two things can come and join up to form a triple bond. The non-bonding electrons will get out of the way and move to the back, and then in between our nitrogens we will have 6 electrons being shared. That gives each nitrogen an octet of 8, and it has a triple bond. A triple bond is a very, very strong bond. That is described as a linear molecule. Ethine has the formula C2H2. So every carbon is connected to one hydrogen, and then the carbons must be connected together. So we have our hydrogen, which wants to share 1 electron, and we have our carbons that want to share 4. So we have a carbon that is attached to a hydrogen at one end, and a carbon that's attached to a hydrogen at the other end, and then in between must be the electrons of a triple bond. So here are my hydrogen electrons. Carbon will share 1 electron with both of those hydrogens, leaving it with 3 electrons to share between the carbons. The sharing of those 6 electrons is a triple bond. So we have our structure, which again will be linear because it is a straight line. Hydrogen cyanate has the formula HCN. Now, when we read this formula, we know that hydrogen shares 1 electron, carbon can share 4 electrons, the nitrogen can share 3 electrons. What will generally happen is the atom with the most electrons to share will be in the middle, and it will be bonded to the other things. So we'll have our carbon in the middle, our nitrogen on one side, and our hydrogen on the other side. The hydrogen is the easy one. It wants to share 1 electron, so the carbon will happily share 1 electron with the hydrogen, giving it a single bond. That leaves 3 electrons left over, and nitrogen wants to share 3 electrons as well. So carbon will happily share 3, nitrogen will happily share 3, giving us 6 shared electrons between the carbon and the nitrogen, which is a triple bond. So we have H single bond, C triple bond, N. Again, it will be linear because it will be in a straight line. Moving on from the models, we need to be able to explain some of the properties of electrical conductivity and state at room temperature. Now, electrical conductivity. Covalent molecules contain molecules. Molecules do not have freely moving charged particles, so they don't conduct electricity. There is one exception. Graphite, which is made up of just carbon atoms, has a delocalized or a lone electron, which can move freely through the molecule. So graphite is an exception for a molecule that can conduct electricity. Most other molecules, all of the electrons are shared. The electrons are not free to move, so they don't conduct electricity. The state of covalent molecules at room temperature. Well, generally these molecules that we've looked at are small and they are gases. So when you're a molecule and you're small, you are generally a gas, which means you have weak forces of attraction between other molecules. So they tend to have very low melting and boiling points. There are a couple of exceptions. Diamond. Diamond contains carbon atoms with 4 strong covalent bonds. Now that structure is very hard to break down, and diamond is a very strong solid. Water is another exception because it's a liquid at room temperature. Now, water is a special compound that contains hydrogen bonds, which are a strong bond between water molecules. The final thing we need to do is compare and contrast the bonding models. So the 3 bonding models we've looked at are ionic, metallic, and covalent. We need to know what the bonding occurs between. Ionic bonding occurs between metal and non-metal ions. So the ions bond together. The bonding force is what holds the model together. So for ionic, it's the electrostatic attraction between positively charged cations and negatively charged anions. What were some of the properties of ionic? Well, it was a solid at room temperature. It didn't conduct electricity in the solid state, but it did conduct electricity when it was molten or dissolved. Some examples of ionic bonding would be sodium chloride, potassium bromide. There are a number of examples. Metallic bonding. Metallic bonding occurred between metal ions and a delocalized sea of electrons. Those metal ions were in a lattice and the delocalized electrons were all around the lattice. Our bonding force is an electrostatic attraction between metal cations and the sea of delocalized electrons. Some of the properties of metals, well, they're all shiny because the light can bounce off the electrons. They're generally solids at room temperature. They're malleable and ductile. Those are the properties of metals. Generally have a pretty high melting point because there's a strong attraction between those cations and delocalized electrons. Some of the examples might be magnesium or calcium metals. Covalent bonding. Covalent bonding occurs between non-metal atoms. Non-metal atoms that share electrons to form covalent bonds. So the bonding force is a sharing of electrons. What are the properties of covalent molecules? Well, they're generally gases at room temperature, especially if they're small, and they don't conduct electricity as a solid. Some examples are chlorine and oxygen. It's important that you remember the bonding force and what things are part of the bonding and what things do what. The bonding force is very important, and knowing which type of bonding will occur between particles as well. Thanks for watching Year 10s. Don't forget, drop a like on the video, subscribe if you're new, and I'll see you